This is Nathan Smith, Fresno Pacific University, or Economics in Business for degree completion students. Slides for Chapter 14. So this chapter is about risk. And we'll start with the distinction between risk and uncertainty. It's kind of a funny distinction. So the risk situation where there's more than one possible outcome to a decision, that's the same here. Situation where there's more than one possible outcome to a decision. The difference is the probability of each outcome is known versus the probability of outcome is unknown. I don't think this distinction has that much of a basis in natural language, but economists will use this, will make this distinction. But it is worth thinking about. So if you know the outcomes, that's one situation. They call that risk. If you don't know the outcomes, that's another situation. We call that uncertainty. In practice, of course, you might have some idea about the outcomes without knowing exactly what they are, but we sort of simplify it by splitting it into these two cases. So, so even the biggest companies can fail. This shows a number of very large companies that have failed at one time or another. This underscores risk. If you're the bondholder in one of these companies, you would have lost all your money. So, if you were a shareholder in one of these companies, you would have lost your whole investment. Bondholders sometimes did get some money back, but it's a reminder that there's a lot of risk in the world, and or a lot of uncertainty. Okay, so we'll start by talking about measuring risk. Think of risk as a probability distribution. So there's a lot of different outcomes that might occur, and the probability that different outcomes will occur is somehow distributed over the different outcomes. So the probability is the chance that an event will occur. The distribution is a list of all the possible events with the probability that each will occur. And this formula, the expected value or expected profit, the bar just means sort of the average, and you notice what you do here. Do a summation, or 1 to n. N is the number of different possible outcomes. These pi, that's the probability. Sometimes P means price, but not here. Here P means probability that event I will occur. And then in each case there will be some amount of profit that will be made, so that's multiplied by the probability. Profit is multiplied by probability for each outcome, and that gives you the expected profit. Notice that the sum of all the probabilities will add up to 1. So this is a weighted average of profit under the various possible circumstances. So that's expected profit. So, for example, probability distribution about states of the economy. This is something we often might not know about. Maybe there'll be a boom, maybe there'll be normal economy, maybe there'll be a recession. So if you're making a business plan, you're thinking about the future, you're not sure what the economy is going to be like when your investment matures, starts generating revenue. So we can assume the probability is 25%, 50%, 25%. This is just rough figures, of course, but to some extent we would be able to guess this on the basis of history. Or there's also companies that would create forecasts. So now suppose we have some project. We have two projects actually, A and B. Project A, both projects return more in the boom, you notice. And in a normal economy, they return the same amount, 500. But in a boom, then Project A returns 600. Project B returns 800. In a recession, Project A returns 400 and Project B returns 200. Now, same probability distribution, because whether it's a boom or a recession isn't going to depend on which project you pick here. The company's much too small to influence the state of the economy as a whole. So what we do is we multiply 0.25 by 800, 0.5 by 500, 0.25 by 200, that gives us this one, 0.25 by 600, 0.5 by 500, 0.25 by 400, that gives us this one, adds up to 500, adds up to 500, and so you notice these two projects have the same expected profit. So keep these in mind because we'll keep looking at the same projects. Question, how about risk? Which is riskier? Same expected profit, which is riskier? Okay, so so we can think about risk in terms of probability distribution. There's a distinction here between discrete and continuous. This is kind of similar to if you know about CDs and records and tapes and stuff, the difference between between digital and analog. So digital is the same, is discrete is kind of like digital. There's just a certain fixed integer number of possible distributions. Continuous, it's a continuous range of events, and it's an interesting sort of theoretical difference between these two. I mean, sometimes you might break up a continuous distribution. You could say, well, it might be between 5 and 6, it might be between 6 and 7, it might be between 7 and 8, and you can make those ranges. Then you'd turn a continuous distribution into a discrete distribution. A lot of things would be, if you think how much rain is going to fall next year, that'll be a continuous distribution. If you think how many cars are going to pass this street corner within the next 15 minutes, that would be a discrete distribution, because it doesn't make any sense to say, well, 0.7 cars will pass. So rain, that's continuous because it's, it could be 5.7 inches or 26.234 inches or whatever. So that's a continuous distribution. So I guess it's a sort of a simple distinction, but it can get confusing with all the applications of it. Anyway, so the project that we talked about a moment ago, we had a discrete probability distribution that was described for us. In practice, maybe a continuous probability distribution might be more realistic, but we're going to treat it as a discrete probability distribution. So 3 possible outcomes, 400, 500, 600, 3 possible outcomes, 200, 500, 800. So you notice project B, these seem to be a little bit more spread out than for project A. So now what's been done here is these have been converted into continuous probability distributions. Of course, they don't express the exact same values as the previous one did, but I think this is sort of the assumption. Okay, let's suppose you're not really, first of all, there's not just a boom normal economy and recession. There's a lot more detail. It could be a a little bit stronger than normal, or quite a bit stronger than normal, or a super intense boom, and so on. And also there may be some and the profitability of your projects might depend in a continuous way on the state of the economy. Anyway, if that were the case, then we would have to draw these as continuous distributions, which are in some ways maybe harder to analyze, but it's important to understand both. Okay, so if we know the probability distribution and we want to measure risk, then we can start with what we'll call an absolute measure of risk, the standard deviation. I think I've talked about standard deviations before, so this is kind of a review, or maybe adapting a little bit. So again, standard deviation is each observed variable minus the mean times the probability distribution. So this mean is the same thing we saw before. It's this. This is just we've substituted x for pi, but it's the same idea. You calculate, and one thing that's a little bit different than what we're doing, we're weighting the outcomes by the probability. So we didn't really do that previously with the observation. Now we are. So with the standard deviation 2, we're weighting by the probability. It's a summation over all possible outcomes 1 through n. The deviation from the mean, this is squared. And then after we weight it, then we take the square root. That gives us the standard deviation. And the standard deviation, absolute measure, it means it's actually in the same units as the variable that's measured. It's in the same units as x. So that's sort of makes it easier to, I guess, interpret. So with the projects that we looked at, okay, we know the mean, 500. Take 600 minus 500, 500 minus 500, 400 minus 500. Then we square both of these. We get 10,000, 0, 10,000. Multiply them by the probabilities. It gives us 2,500, 0, 2,500. We add those up. We get 5,000. Take the square root of 5,000. That's 70.71. You notice this is in the same units as, so in this case the mean profit is 500 with a standard deviation of $70.71. And once you get somewhat accustomed to statistics, you can talk about standard deviations. It's kind of a shorthand for explaining how much dispersion there is in some particular variable. That becomes sort of a convenient way for people who are statistically savvy to talk to each other. Now, let's do it for the other project. 800 minus 500, 300. 500 minus 500, 0. 200 minus 500, negative 300. Square both of those, 90,000, 90,000. Multiply them by the probabilities of the three states of the world, and we get 22,500, 22,500. That adds up to 45,000. Take the square root, 212 and 13 cents. So this is a project with an expected profit of 500 and a standard deviation of $212.13. This project is riskier. That's what the standard deviation tells you. You can't get that from the mean. The means are the same. But you can get that from the standard deviation, which project is riskier. So the standard deviation serves as a measure of risk. Now, statisticians will put a lot of stress on this particular distribution. This is called the normal distribution, and it just tends to pop up a lot. There's something called the central limit theorem that if you add up sources from a lot of other distributions, they'll have a tendency to converge to a normal distribution. So that kind of explains why the normal distribution is so important. Don't worry about that too much though, but mainly we're just frequently going to assume that this normal distribution is always at work in lots of situations. Well, if it is, one standard deviation in either direction, that gives you 68.26%. That means that's how likely the value is to fall within this range. 95.44, that's the probability that it'll fall within 2 standard deviations. 3 standard deviations, 99.74%. So, and with a normal distribution, it could go infinitely out in either direction. That's part of the definition of a normal distribution, strictly speaking, which is why things like human heights can't strictly be normally distributed, because you'd have to have people with negative height. So could you get something with 5 standard deviations from the mean? Could happen, but it would be very unlikely. If the variable is normally distributed, which is frequently a reasonable assumption to make. So that gives you some idea what the standard deviation means. If someone says profits are 500 with a standard deviation of 70.71, someone who's statistically savvy will kind of have this sort of chart in the back of their minds. They'll know, okay, that means that it probably falls within 1 standard deviation, and it's almost certain to fall within 3 standard deviations of the mean profits. So that's what that means. Now, you notice that in the example we were using, then the average profit was the same for both projects. But if you're going to compare 2 projects, let's say one project is really big and one is really small. Well, you wouldn't really want to say. You wouldn't really want to say that the big project is equally risky as the small project if both of them have a standard deviation of 100. If the big project has an expected profit of 100,000 with a standard deviation of 100, and the small project has an expected profit of 100 with a standard deviation of 100. Well, the small project is pretty risky, really, and the big project is very, very safe. Is not very risky at all. Well, in order to sort of compensate for the size of the project, we could just take the standard deviation, divide it by the mean, and that gives something called the coefficient of variation. We call this a relative measure of risk, so it's relative to the project. So that's something else to know. So lots of statistical values. We could give you more, but these are kind of, the standard deviation is key. Coefficient of variation maybe a little bit less important, but would be appropriate for comparing projects of different sizes. Okay, so now utility theory. Utility theory is a really cool field which we will not get into that much in this course, but we're going to talk mainly about utility theory as a way of understanding risk. So people can be risk averse risk neutral, or risk seeking. These are kind of a typology of people, and there's degrees of risk aversion and degrees of risk seeking. So risk averse, you have to be compensated for taking on risk. So in the projects we talked about, we had two that have the same expected profit, but one of them is riskier than the other. So if someone's risk averse, then they would prefer to take the less risky project. And if you want them to take a riskier project, it would have to have a higher expected return to compensate for them for this. Now, this sort of magical language, diminishing marginal utility of money. Well, utility means kind of the pleasure or the value that you put on things. And so money, of course, is the return. The idea is you get pleasure, you get value from money. Marginal utility means how much value do you get from the last unit of something, in this case money. And then if you say this is diminishing, that means that if I give you $1, then I give you another $1, the second dollar makes you more happy than the first one. It increases your happiness less than the first one increased your happiness. And if I keep giving you more and more dollars, probably if you have only $10 to your name and someone gives you 10 more dollars, then you'll be pretty happy about that. If you have $1 million, then you don't really care. You're slightly happy about it, but very little. You get much more marginal utility from when you're poor from $1 than when you're rich. And so this is the idea of risk aversion, diminishing marginal utility. This is probably the most common case, risk aversion. Risk neutral, that may be a common case too. That's when you're just indifferent to risk. That's probably the case if you're smart and the amounts of money in question are very small. So if you're making a $10 bet, then you should probably be risk neutral. If there's even the slightest, even the chances are even slightly better than even that you're going to win that bet, that's probably worth doing, because $10 more or less is not really going to affect your lifetime income in any significant way. So you don't really need to be risk averse when it comes to something like that. Risk seeking, this is one is a little bit strange and weird. This is the idea that people actually like to take on risk, and sometimes people would just say, well, they're just crazy, they're just irrational, they're just not estimating the risk properly, and maybe that's often actually the case, but economists like to credit people with rationality whenever we can, so then we would say, no, they just have a different utility function. They happen to have an increasing marginal utility function of utility of money. And there could be certain cases in which that might make a lot of sense, but it's certainly not typical. So we can represent this graphically. Okay, utility on one axis, vertical axis, on the horizontal axis, money or wealth. So diminishing marginal utility is this one that it goes up, and then it still goes up, but it goes up less steeply. Sort of the hill is initially steep, and then it becomes less steep. That's diminishing marginal utility. Constant is just a straight line, and increasing curves the other way. So this person's really happy if he gets to 6. It doesn't benefit as much from the first. If he gets to 20,000, he's really happy. He's not as interested in the difference between 1,000, 2,000, and 3,000. Okay, so let's apply this to a manager. Manager's making some sort of a business decision, and the manager, will suppose, has a utility function. Now, why the manager might value outcomes in different ways is a long story. Maybe he's happy with his situation, and as long as he keeps it, he'll feel okay, but if he loses money, he might lose his job. That's bad for him. Making huge amounts of money doesn't do him that much good because he still just keeps his job. You could have a lot of different stories for why the manager's utility function might look like this, but the way we describe this utility function is the manager's risk averse. So, and this is just sort of a quirk. Sometimes it happens that people will buy insurance and also gamble. Sort of strange. Doesn't seem to make sense. Say, so not having insurance is a little bit like gambling. The difference being that getting insurance, you have to pay a premium to the company. Gambling, you also have to pay a premium to whoever is providing you with the opportunity to gamble. So in this case, you're both taking on extra risk by gambling and trying to get rid of your risk. And in both cases, you're paying somebody to have this option. That seems really stupid. Well, it turns out you can actually rationalize this if you figure that people have this kind of strangely shaped utility function. I don't think there's much reason to think that many people do. Probably people are really just being irrational. But if you want to insist they're rational when they gamble while buying insurance, then you can say they have a utility function shaped like this, and then their behavior would make sense. Okay, that's just it's sort of a quirky, just demonstrate sort of what utility theory is capable of. Because utility, nobody can really see it. You can't see it directly. You can only infer it from people's behavior. That's the art of this. And so, when you look at people and they're like, oh, he's buying insurance and he's also gambling, that doesn't seem to make sense. But if you're good at inferring utility functions for people's behavior, you're like, oh, no, we can make sense of that. So, anyway, okay. So, how can risk aversion affect decisions? So remember, we're using this utility function. We can look at probability of a particular outcome taking place. Say it's 40% chance of success, 60% chance of failure. Is this project worth doing? Well, if you just look at the expected return, it looks like it is worth doing. 8,000 is the payoff to success times the probability of success. Negative 6,000 is the penalty for failure times the probability of failure. Added up, you get 2,000. Okay, but now suppose the manager has this utility function where he says, okay, my utility from making $20,000 is 3. My utility from losing $10,000 is negative 4. Whereas these are sort of disproportional. So he likes making money, but he doesn't like making money as much as he dislikes losing money, even if it's a smaller amount of money. Okay, so now we multiply 40% times 3, 60% times negative 4, and he ends up with negative expected utility. So from this manager's point of view, this project isn't worth it, even though its expected profit is positive because it's too risky. He's risk averse, so he declines the project. Let's see how long I've been going. And yeah, that's probably enough for now.